Hi everyone. Today is day 9 of our challenge. And if we go to the list, the problem for today is to work on SimCLR, self supervised learning, or GPD based text generation project. We are going to split it into two. In part 1, we are going to do it today, and part 2, we will do tomorrow. So I'll copy it and then use the same ChatGPT window. And I'll say, hey, it is day 29 and the challenge and the problem is problem statement is this. Uh, Today we will work on uh, will work on part 1 of it and tomorrow part 2. Let me move this to here, and yes, let's wait for it to generate the response. And it says great, for day 29 you have the option to work on either self-supervised learning technique or GPT based text generation. Since this is split into two parts, today we can focus on setting up the project either by building the architecture, preparing the data, or starting with foundational components. And tomorrow we will continue with training or further exploration. Perfect. So let's explore both project option briefly and to help you decide. Okay, let's go through both the options and decide. Then we can decide. Uh, just a second. Let me open the window for my cat. The my cat is becoming a little paranoid. Let me now close it so that you don't hear the background noises coming out from the window. So okay, the option one is self-supervised learning SimCLR framework developed by Google for visual representation learning. Okay, it works by learning effective representation of images without needing labeled data. Okay, the basic idea is to use constructive learning, contrastive learning, where the model learns to differentiate between positive parts, different augmentations of the same image, and negative parts, different image. And second is GPT based text generation. GPT based text generation is generative pre-trained transformer, is a language model designed for text generation. It can be used to generate coherent paragraphs, summarize text, or even generate creative writing. Today we would set up, if we would go ahead with this option, we would set up the GPT model, prepare the data. Tomorrow we will train on the data set and generate text output. If you remember, we have done something like that. If we go back to the problem, like where we have used to generate the text for we have done some problems like that. um, Given, now it says that given these two options you could pick whichever one aligns better with your interest. If you want to explore explore computer vision and learn self supervised representation learning, go with SimCLR. If you prefer working with large model generating human like text, go with GPT based text generation. I don't know which one should we go ahead with. I'm just feeling that let me read a little more. It says that here's how each project would proceed in the project one, where we sim learning part one. We will load the data CIFAR 10. We have used an ImageNet. We have used both of the data set a lot in a lot on many of our problems, like problem number day number 5 we have used it, day number 8 we have used it, so we know what this data is about. Then we are going to apply multiple augmentations like random crop, flip, color distortion, etc. Implement or use sim color architecture including encoder, Typically ResNet, we have I feel like we have explored ResNet before. When we were doing computer vision, we have explored the ResNet before. So I'll go computer vision, we were doing it computer vision here only. So I guess we have, here we have used, so I'll go here, and ResNet we might have. So I feel that we have already explored this ResNet um, type problem. And then, so this is more of a computer vision related problem where we see something something generated. And then the second one is more related to the text data set. So where we will load the data set, Shakespeare one or IMDb movie scripts, tokenize the data, prepare the sequences to train the GPT model, load the pre-trained GPT-2 or GPT-3 model using Hugging Face Transformers library, and prepare it for tuning. It might look like that we will be doing something like what we did yesterday and day before that, but I'm feeling like probably we could go ahead with this sim CLR for today, a simple framework for contrastive learning of visual representation. So I feel we could go ahead with this one. I think I should go ahead with something different today. We have been doing a lot of problems on related to text generation in the last week. So yes, I decided to go ahead with the with this option one. Cool. Thanks. I decide to go ahead with option one. SimCLR, simple contrastive learning of visual representation. Simple framework for contrastive learning of visual representation. So what it says, let's wait for it to generate the response. Okay. Uh, okay. Awesome. So let's start. So it says CLR is a powerful technique in the field of self-supervised learning. Okay, especially for visual representation learning. Today we will set up the foundational component for SimCLR, which is self-supervised learning, which is the full form is simple framework for contrastive learning of visual representation. Um, Okay, which means what are we going to do? We are going to prepare the data, implement augmentations, build the architecture. Tomorrow we will work on training and evaluating the learned representations. Okay, so SimCLR works by generating different augmented version of an image and then training a model to pull these augmented views close together in the latent space while pursuing other different images part. Okay, so how we are going to, so the how it is going to work, so it is going to generate different augmented versions. And how we are going to augment, we are going to augment with a lot of operations. So we read it just now, but if we come here we can see that we might do cropping, resize, flip, we change the brightness, we adjust the contrast and also by doing all of that we augment the image. um, and then yes, we'll augment the input image, and then we'll train the model to pull these augmented views close together in the latent space while pursuing other different images apart. Okay, so what are we going to do? We will do first load the data set. So which data set are we planning on using? We are planning on using the CIFAR 10 or smaller data set for simplicity. I think we can go ahead and use the CIFAR 10 dataset because we have already explored that dataset, so it will be easier for us to not get lost in a new dataset. So, and then we are going to apply transformation like crop, color distortion, and flipping. Then we will implement the SimCLR components. We will set up encoder and projection head. Okay. And then I'll be doing what? Define the loss function, which we will use tomorrow. Which we will use tomorrow. Okay, so let's get started with the implementation. So the step number one is we will begin by importing the necessary libraries. Let's start. I think we should go ahead. I am okay to go ahead with the code because I understand this what the model is about. Not in depth, but I do understand what we are doing. So I don't think anything is alien to me right now. So let's do what? Close it, and do what? Open a new Python file, name it as day2930.py because we are doing coding everything in coding a single problem in day 29 and 30, so that is why. So it is going to be problem is just a second, just a second. Sorry, so I've resumed it, let me check. Okay. Sorry. So yes, I'm back. So let's start with importing the files. And the files are going to be import TensorFlow as TF. And then what are we going to import? Layers, dense layer, global average pooling 2D layer. ResNet we are going to import. So let's import from TensorFlow.keras light keras dot what layers, import dense layer and global average pooling TD. Then the ResNet application from TensorFlow keras application, import ResNet. We have used it already, so I would recommend for you guys to go and check that out. Then we are going to import the add-ons, which is TFA. I don't know what that is. I'll wait for the code to explain about that. If not, we'll come back and explore that. TensorFlow add-ons. So it is going to be Tensor TensorFlow add-ons. Are we using it anywhere? Because what it does, it we are not using it anywhere. We are not. I guess we are not using it anywhere. Loss function. Are we using it anywhere? Let's wait for it to tell us that we are using it anywhere, and if we are, then I'm going to import it. It says that it provides extra functionality including some useful loss functions, and then numpy and matplot py plot. So import numpy as np, import matplot. Okay, I have not installed it yet, so I might have to install. Why do you think I have not installed? Because if you remember, day before yesterday, on I guess day 26, we did face a lot of challenges with installing the transformers lab package, which and I had to upgrade my Python to 3.10. For that, I had to change my Python environment. So that is why I'm installing all the packages again. So I'll say pip install matplot library, and I'm just going to come back while it is doing that because my mother's voice is coming in the background. I'll say okay, I have already closed the gate. Even then, if it is going to come, I cannot help with it because I'm not a YouTuber making doing it professionally. I'm just doing it for a different reason. I'll say import matplot library py plot as plt for visualizing, for plotting graphs. Let me clear the terminal and minimize it so that we can see the uh, code, the window where we are going to code. So let's do what? Let's load the CIFAR data. So we will use CIFAR dataset for the implementation. It is a commonly used dataset for images. What it does, it has images classified in 10 categories. And when we will be importing them, those categories are labeled with digits from 0 to 9. So yes, and we have already explored that part, so I'm not going to go and reinvent the will do that again. If you are interested, you can do it yourself also. I don't want to be rude, but you can go and check out the video on the I guess day 5 video. There we have explored it very nicely, what this and how this data looks like. So coming back to the code, we'll load the CIFAR 10 data set. So we'll now save that in X train. We'll not save it here, and then we'll have X validation. And for training, for the target, we will not need, I guess, target. So it is going to be what data set are we going to CFS. So let's load it here only. I don't want to clutter here with specifying the library. So I say import from TensorFlow keras data sets, import CIFAR 10. So I'm going to import this CIFAR, call this CIFAR 10 load data. It has loaded the data, and then we are going to combine the training and test data. We will do what? We are going to combine the data. Combine the training and test data. So why we are doing it? Because for we are concatenating the training and test data, because SimCLR is a self-supervised learning technique and we do not need the labels for training. Okay. In self-supervised training, we don't need labels for training. Training technique super SUPER supervised, we don't need label for training. So we are doing what? Concatenating. So what are we going to do? Concatenate. So X data is going to be numpy dot concatenate X train and X validation. Perfect. And we are going to concatenate column wise. So sorry, row wise. Okay. And then so like this, in a row we are going to concatenate, and then we are going to normalize. So these are the normalized data. This will help in our activation function that we are going to use. We will be using 10h activation function. We know that with 10h activation function, it works with values from between -1 to 1. So we are going to normalize it between that range, and the pixel values in that for the images in this dataset lies between 0 to 255. That is why we are doing it that way. So we normalize the pixel values between -1 and 1, helps with 10h activation function. Okay, and we are going to do that. Okay, and now let's do normalize it. X data is going to be X date data dot converted to float 32, and then divided by 127.5, 255 by 2, and minus 1.0. Okay, and let's go to the define augment. So now we are going to define a function, a helpful function, which is going to apply the augmentations, like crop the image, resize the image, flip the image, adjust with the brightness and contrast. As we have just read that SimCLR requires heavy data augmentation to create multiple views of the same images. To create what? Multiple views of the same images. So that is why we are creating this function. So let's do what? Define the augmentation. So this is augmentation, not augmentation. So we'll do define data augment. So here we'll say image, and here we random crop and resize. So random crop and resize. So image will become what function? Okay, TensorFlow image crop random crop. What scale are we cropping? Size 28, 28, 1. Image 28, 28, 1. Not 3 channels. And then we'll do what? Resize into 232 by 32. So image will become TF image, resize the image 32, 32. Okay, then we are going to randomly flip left to right. Random flip left to right. So it is going to be okay. Image, which function we are using? The random flip left to right the image, and then we are going to do color distortion. Color distortion. So we are doing that, and the image is going to be image dot adjust. So brightness random brightness, and we will at max it is going to be 0.5. Image max delta is 50%, and then we will adjust the contrast. Lower will be 0.1 and upper will be 90%. So image TensorFlow image random contrast of the image. Lower will be 0.1, upper will be 0.9, and return the image. Perfect. Now we visualize some augmented images, and we visualize some augmented images. So let's do what? It creates a subplot of one row, four columns, and the size of the figure is 10 is to 3. In the we then will range from 0 to 4 for to depict those four cells, and then we are going to use the pass the uh, random random image from data augmentation to random image to the data augmentation function, generate the image, and then we are going to show the image using the IM show function. uh, Now we are going to rescale it back to 0 to 1 using this img plus 1 divided by 2, and then we'll turn the axis of the x-axis and y-axis, the numbers on them, and show the image. So let's do what? Let's mention the figure and the axis and get the plot subplot 1 is to 4 figs subplots, not subplots. Okay, and just a second, there should be some background noise you must be hearing. I'm so sorry. Again, some background noise. My father was doing some. Yeah. So let's start. Uh, yep. So here we have to mention what size. So the size of the figure is going to be plots of plots. Figure size 10 is to 3, and then we'll get the figure. We'll go to each cell in range 4, and then we'll do what? We'll get the image, we'll get the randomly generated image, pass it to the uh, so you'll use pass it to our data augmentation function to do some augmentation on the image. We will use numpy dot random dot random int, and we have to generate to x data. This will generate a random number. Why? How about this? We generate, so it will take some random number, give us the image, and then we'll do what? Will from the axis, that is the all the from the figure, in each axis we are going to show the image using imshow, and we will rescale it back to 0 1, that is rescale it back to 0 and 1, and then turn the axis off, and then just show it. Let's do what? Let's run it. We want to see some random 4 images, date 29/30. While it is doing that, let's go and see if we need anything, what all we need for the rest of the steps. This is going to be pretty easy. This will also be a little easy, and then we are done. And we have an error. The error is on line number 12. It says that the error is too many values to unpack. If I go here, we have used it already. Oh, sorry. The problem is with this. Let's run it again. I had a typo, I did not mention it here. Okay, so these are some random images. This is of a bird, this is of a horse, this is a ship, this is of a frog. So let me take a screenshot, close it here, and run it again. Horse, a duck, I don't know what that is, a train, I guess. So yes, it is generating 4 different images whenever we are running. So cool, it is doing all sort of contrast. This is of a cat, bus, elephant, and a parrot. So really cool. We are able to successfully run the step number 3. Now what we are going to do? We are going to do set up the base network. So we create encoder or set up the base network. So let me go and minimize this. So I'll come here, set up the base network, that is encoder. So we are going to create a function for that, define create encoder, and then we will use the resnet 50. We know what this is, we have used it in one of our previous problems. So this architecture is a common choice because of its strong execution extraction capability. This is a pre-trained model, heavily trained on a large data set, so that we are going to use it. We will mention that we want the don't want to include the top. We are going to add with our custom layers, which data set it is going to use, ImageNet, and then input shape is this. So let's use the base model. Base model is going to be ResNet, and here we mention include top, no, because we will be adding our own custom layers. Weights, yes, and it is going to be ImageNet, and this what input shape is going to be, if you remember here we did it to 32, right? So we'll use the same 32, 32 and 3 channels because it is a colored image. And then we are going to mention, okay, the base model should be trainable. Is it? Yes. Why? We want to train the base model from scratch. Okay, we want to train the base model from scratch. Okay, then we'll take the inputs is going to be from terrace carest inputs. We'll add an input layer. Here we mentioned, let's add it, the input layer. The input is going to be in the shape of 32, 32 and 3, and then the base model is, here we mention the input that we have created, and the training, yes, do we want it to be trained? Yes, true. And then we are going to what, add a global average pooling layer to do what, to extract. You remember why we do pooling, right? We have explored it in the, when we were understanding the scene and what convolutional neural networks are. We understood that why we add the pooling layers, because we want to extract in the most important features. So we are going to add the global average pooling layer, which is, here it also says, I did not read it, remember. So this is how the full whole the challenges are helping me. So this, after extracting features, we apply pooling operation to reduce the dimensions. So here we meant, this is the input for this layer is going to be the previous layer, and we will return the uh, TensorFlow keras model, and here we mention inputs and the layers, and we create encoder, save it into this encoder and variable, and do what, print the encoder summary. Now we are on the last step. No, this is not the last step actually. So now we are going to do what, we are going to define, not here, yes, now we are going to add a project head. So SimCLR uses a projection head, typically 2-3 dense layers, to project the output features from the encoder into a new space where the contrastive loss is applied. So this is where the contrastive loss will be applied. So we'll take the input layer from the encoder, produce the output layer, add the output layer with 256 neurons, activation function, rectified linear unit, and then we'll have a 128 neurons, output layer with 128 neurons. The projects the dense layer 256 is because it projects the output into lower dimensions. Activation is this. Then we output a 128 dimensional vector that will be used for contrastive learning, that will be used for contrasting learning, and then we will return it. So we'll do what? Create contrast project head. uh, Create project head. So we'll do what? Definitely not definitely, definition is create project head, and then we input is encoder dot input, not inputs, input, and then we create a layer from the encoder, output layer, we train on that. So first we add a dense layer with 256 neurons, activation function, rectified linear unit. The input for this is going to be x, the previous layer. The final layer we are going to be dense layer of 128 neurons. Final layer you will be used for contrast, yes, learning. Okay, and then for this the input, the previous input layer for this dense layer is going to be, the output layer is going to be the previous layer, and then we return keras model and mention inputs, output. That's it. Just a second. Sorry, someone was at the door. Okay, so now we'll do what? Create the project head. So the project head that we had detached is going to be created, and then we will print project head summary, and let's do what? Define the contrastive layer that was returned from the project head. So the contrastive layer loss encourages the model to bring similar images closer while pushing the apart the dissimilar images. Okay, so what it does, it brings the similar images closer and pushes the dissimilar images apart. So we will define the contrastive layer. Define the contrastive loss. So we'll do what? Define contrastive loss. Here we mention, here, hang on, here did not mention the encoder, right? So here we have to mention the encoder, right? And then yeah, sorry. So here we take we normalize the projection to make dot products between the vector equivalent to cosine. Okay, so we will use cosine similarity to find the similarity between the two vectors zi and zj. So we will do dot, so we will normalize them uh, by making the dot product between the two vectors. Then we will do what? We use cosine similarity to find the similarity between the two vectors. Then a temperature is a hyperparameter that controls the smoothness of the distribution, correct? Then we have similarity matrix. We if you remember, we have explored how this cosine similarity works in one of our problems from the machine learning challenge. Just a second. Okay, so yeah, we will do compute the similarity between the every pair of vectors, and then we will do cross entropy loss. Is So the loss is computed in a way to maximize the similarity between the positive pairs and minimize it for the others. So we will use cross sparse cross entropy to calculate the loss, and then we would return it by using the reduced mean. Okay, let's code it up. So what are we doing here? We are getting two vectors, zi, zj, and the temperature is 0.5. It is used to control the smoothness. Uh, sorry, of the distribution. So we'll first normalize the two vectors. Normalize the two vectors. So first we'll do what? Zi will normalize using the math. L2 normalization, zi and x is 1, zj tf math, L2 normalization, normalize zj x is 2, and then compute cosine similarity, compute cosine scores. So we'll do what's create a similarity matrix, and let's move it to the center, and do what? Use TensorFlow multiplication of zi zj will compute the dot product of the two vectors, and transpose p true, not here, and then we'll do what? Create logits, create a similarity matrix, and we what are we doing? We are creating logits, and then we'll label our indices of. I'm just curious to know what these are, so I'll go and ask, can you explain here what is L2 normalization and logits? And then we are getting the batch size, we are getting the labels, and this we know in easy and short, in easy language and short. I've seen it that it tends to explain too much which is not even required, so that's why I have explicitly mentioned it to keep it short. So L2 normalization means we scale the vector so that their L2 norms or the length is equal to 1. We normalize the vector such that their length becomes equal to 1. Imagine each feature vector, which is z underscore I, z underscore j, as a point of high dimensional space. L2 normalization makes each vector have a magnitude, that is the length of 1, but it keeps the direction of the vector. Okay, why do we do this? By normalizing vectors, the dot products between them becomes equivalent to cosine similarity. Okay, we are doing it because it is required for computing the cosine similarity matrix. It is very helpful for contrastive learning where we want to compare similarities between different parts. Okay, and logits refer to unnormalized similarity scores we compute between the. So it is an unnormalized similarity scores we compute between the pairs. That is why we divided it by the temperature. In the function, logits are calculated by the dot product of the two normalized feature vectors zi and zj, which gives us the similarity matrix, similarity measures between all the pairs. Correct. It will give us the similarity measure between all the pairs. Type temperature is a hyperparameter that controls the sharpness of the similarity scores. Dividing by the temperature makes the logits less extreme. Yes, if the dot products is too extreme, how do we normalize them? How do we so we do what we divide by the temperature to smoothen it. To if they are too extreme, we make them less extreme by dividing by the vector, so that the model can better learn the similarity between positive pairs and distinguish them from the negatives. These logits are used directly as inputs to soft. Okay, so these logits will directly be used to the softmax function, which then convert them into probability. We know that what softmax function is. It outputs in the form of probability. So these logits will be useful for the softmax function. So what I understood is that it is helpful for unnormalizing. It is helpful for softening. It is helpful for making the logits less extreme, making the dot product of the vectors less extreme. Uh, okay, so we understand that. So we have already computed it. Let me go back to the not here, not here. Yes, the code. Here we get the labels and the indices of the positive pairs. Labels and indices of the positive pair. So we'll do what? The batch size is TensorFlow shape. We shape it the the first vector. We get the shape of the first vector. This we get the shape of the first vector. This is going to be the batch size, and the labels are TensorFlow range in this batch size. And we'll do what? Calculate the cross and calculate the cross entropy loss. I am really interested to know how these will look like. So I'll ask, can you explain this as well and show how they would look like? So this will return the shape of the tensor vector zi. 0 is used to access the first dimension of the vector, which in this context represents the batch size. Okay, that is why we have used 0. We have used this because we wanted to mention I have used it incorrectly. So this is the shape of the first vector, tensor vector, and then we are going to get the first dimension, which is what? Which is the which represents the batch size. The batch size is the number of samples proceed at once during a single pass through the model. In case of training, batch size is the subset of the data set. So it is going to be, for example, if the batch size here is 32 and 28, so it will output 32. Now we'll get the label for the batch size. This function generates a random sequence of numbers ranging from 0 to batch size minus 1. So this will generate a random sequence of TensorFlow numbers between 0 to batch size minus 1. So it will output in this form. And the purpose of this line is to create labels for the positive pairs of images within the batch. Okay. Okay. And why are these important? In contrastive learning, each image in the batch has an associated positive pair, another augmented version of the same image. Correct. The labels generated here are used to indicate that each image should match with a particular other image in the batch. Okay, so we are assigning labels that we are generating randomly between 0 to batch size minus 1, and we will assign it to the images. And these labels will be used to identify that this is the image that it has come from, because we are going to apply a lot of augmentation, right? So this is why it is needed. And these labels are passed to the cross entropy loss function to tell the model which pair are positive and which pairs are negative. Okay, understood. Let's go back, pass it to the cross entropy softmax function. So we'll do what? Calculate the loss of TensorFlow new NN neural networks parse softmax cross entropy with logits, and here the labels is going to be the labels. The logits are the logits that we have created, and we return the reduce the mean of the loss, right? And that's it. And we'll do what? This is we how we'll create the constructive contrastive loss. Okay, cool. So this is where we'll close this video, and we'll come back tomorrow and resume from here.